We've added an I2C interface to the R32V2020 RISC CPU. Let's take a look at how we did it. For the I2C slave, we're using the I2C IO-8 card. It has an 8-bit I2C port expander on it. 4 of the pins are connected as inputs to headers with pull-ups on them, and 4 of the pins on the I/O expander are connected up to LEDs, so it's a fairly easy piece of code to read and write off this single card. Here's a list of features of the card from our wiki page. The card also has an I2C interface with a base address of 20, which can be set with jumpers to addresses from 20 through 27. It has an interrupt LED. It also has that interrupt line routed to one of the I2C or to the I2C connectors, and there's a pair of connectors that allow you to daisy chain between cards and have multiple cards. It's in our ODAS 49mm square form factor, and it has 4 440 mounting holes in the corners. The card has an EP23008 I2C port expander with the features already noted. It runs at 400 kilohertz in the code we have here, although we did test it at 100 on the way to making 400 work. This is the block diagram of the MCP23008. There are also 16-bit versions of the part, the MCP23017, that we have cards for. All of these are available on our Tindie site. The part has 11 control registers inside of it. Some of these are read-only, some of them have different functions for read and write. But to do what we want to do, we only really have to deal with 3 of these locations: the I/O direction, the I/O configuration, and the output latch, or the GPIO, I guess that's for. Here's all of the register bits that are used. The input polarity allows the part to be set for inputs or outputs. The I/O configuration, we're only using one of the bits for that. And the output latch is where you write data out to, and the GPIO is where you read data in from. On our card, the top 4 bits of the 8 bits are input bits and go to the jumpers, and the bottom bits are connected up the LEDs. So that means we connect those pins or we write to this register as F0 to configure the output and input pins respectively. The only bit we have to set in the I/O configuration register to a particular non-default value is a sequential operation. We don't want sequential operation. We want to stay on the same address when we write to a register. We don't want to have an auto increment to the next register. The configuration registers only have to be written when the card is initialized. They don't have to be written after that unless you want to change some particular configuration thing. I2C bus timing consists of high and low clocks and data on various parts of the edges of the clock and present or not present at various parts of the timing cycle. We first implemented 100 kilohertz timing, but then bumped it up because the part is rated at 3.3 volts to run at the 400 kilohertz mode, and we did get that working. Here's a clock cycle of that 100 kilohertz timing, and you can see it's dead on. And here's a single cycle of the 400 kilohertz with clock on the top and data on the bottom. To write to the output latch requires setting the slave address and then setting the register and then doing the write. So it's 3 I2C transfers that all happen back to back. And here is that timing of the 400 kilohertz signal. The scope shows 390.6, close enough. Here's another shot of the 3 transfers. The first I2C transfer sets up the slave address. The second one selects the ODAT register, and the third one contains the data to be written out. Here's the initialization code to set up the registers inside of the I2C IO-8 card. The first one writes to the I/O direction, or the I/O configuration register actually, and the second one writes to the direction register, and the calls to various functions to write to the control registers or the address register, as well as what control register values have to be set before each transfer are indicated here. So in the first case, an O1 is written to the control register inside of the I2C interface. Then the data is written out. Then an OO is written to the control register, which sets it in idle mode, which says there's more things to do after the next transfer. Then the data of O5 is written out. And then the value to the control register of stop, the O3 is written, which tells the I2C controller that this will be the last transfer and to create a stop cycle at the end of it. Each of these command registers have to be written, or control registers have to be written before the I2C is written, to tell the I2C interface what the next transfer type will be. This piece of code controls the actual transfer, doing the start, write, the idle, and then the stop, and in this case what's passed in R8 is written to the output latch. This section of code initiates a retransfer, which consists of a write of the slave address, a write of the GPIO register, followed by another cycle, which is a write of the slave address, followed by a read of the address that was established in the previous write. That's how you do a read on the MCP 2308. The top piece of code here writes to the data or address register, and the bottom piece of code reads from the I2C data register. The reason the top piece writes to data or address is that the transfer could be to the slave address of the card. The final two pieces of code here are: the top one writes to the I2C control register, and the bottom one is very critical. It interrogates the I2C interface to find out if it's busy or not, and hangs out around while it's still busy. I looked around quite a bit for existing I2C VHDL code and found this reverse U16 project under the MVV project. It seems like it's got a bunch of retro computer projects in it, and it was a better I2C interface than a lot of the other ones that I found. Took a little bit of hacking around with it to try to figure out what to do, and I may have changed a few lines in it, but if you look in our GitHub you should be able to see it there, the version we have. If you want more information, you can see our wiki pages for these products, and we have YouTube videos on them as well. We have a store in Tindie where we sell all of our cards. Thanks for watching our video, and if you enjoyed it, don't forget to like, share, and subscribe.